So far, we've looked at how to find the error of a convergent alternating series using the alternating series error bound. Now, that begs the question, well, what do we do for other types of series that are not alternating? And the answer will be to calculate what we call its Lagrange error bound. But before I talk about the Lagrange error bound, let's take a step back and let's revisit our conversation on Taylor series. So the whole point of a Taylor series is that they use polynomial series to replace more complicated functions. And they're amazing. They do a really good job of approximating values. But oftentimes in practice, it's impossible to add up an infinite number of terms. So instead, we rely on something called a Taylor polynomial, which is, again, just simply a finite number of terms to evaluate a function. The more terms we have in our polynomial, and the more accurate our approximation is going to actually be in giving us a sense of what the actual function is. But again, the trade-off there is that we have to add up an infinite number of terms. So we know that for a function, for some function, that our Taylor polynomial, whatever degree Taylor polynomial we're using, plus the remainder is going to give us the actual value of the series. So just like before, our remainder here gives us a sense of our error, how much our partial sum is off by, or how far that is from the actual value of the function there. Now, the biggest issue here that we have is that since we're not always working with alternating series, we can't guarantee that this remainder here is going to be less than the n plus 1 term, or the next order term. If we recall from alternating series, we just simply said that the next unused term represents the maximum error for that alternating series. But when we have a series that isn't necessarily alternating, we need another way of calculating this error. And this is where we come back to talking about what we call the Lagrange error bound. And the Lagrange error bound simply states the following. It says that there will be some x value, or excuse me, some z value between x and c such that the error, our remainder here, is less than or equal to what I've just written out here. Now let's pause because there's a couple things to digest here. So first off, I want us to make sure that we identify and looking at what we have here, and hopefully this looks familiar to you. And that's basically just the general term for a Taylor series. But notice I'm using the n plus 1 order term. And this is basically us just trying to say the next term after our partial sum has been calculated. So it's the next term in our Taylor series. But if you look at it closely, you'll notice that actually the biggest difference here is that I'm calling this value where we're evaluating our n plus 1 order derivative. We're saying that we're evaluating that higher order derivative, or that n plus 1 order derivative, at z. Now let's pause and make sure we understand what we're saying here. So first off, let me just highlight a couple things. So first off, r sub n of x, this is our remainder, or our error. And what we have here is that x is our given x value, or the x value where we're trying to evaluate it at, and c is where our function is centered. Now, what the Lagrange remainder theorem is stating is that there exists some z value that is in between c. So suppose our function is centered at the c value, and the x value is where we're trying to evaluate the function at. There exists some z value somewhere in here, somewhere within this interval, such that the n plus 1 order derivative evaluated at this z value produces some value m. And what we're concerned with finding is the maximum value. What is the largest value that this m could be? Because the largest value here is going to ensure that we have the largest possible error. If we calculate this term here with the largest possible absolute value of m, then we know we will be able to find the largest possible error. Now, the place where students get the most tripped up when it comes to the Lagrange error bound theorem is that they're so concerned with trying to find this z value. And pragmatically speaking, the whole point of this theorem is to quickly assess how well our Taylor polynomial is modeling the function. So it defeats the purpose to try to really struggle and find this magic z value. The Lagrange theorem is an existence theorem. It is simply saying that there exists some z value such that this m is a maximum m value of this n plus 1 order derivative, so that we can find the largest possible error here. So this may not be fair, but a lot of times when I talk about the Lagrange Era Bound theorem or the Lagrange Era Bound, I actually describe it as the worst possible error, right? This is us saying it's the worst that we could be off by. And I know that sounds kind of mean, but actually it's pretty reassuring, because oftentimes when we find a Lagrange error bound, we're saying, hey, I know that my approximation for my function is going to be no worse, or it's not going to be off by any more than this value. And we'll see in a bit that when we start getting Lagrange errors and we see how good they are, we'll say, hey, if this is the worst that our approximation is going to be off by, then I know I'm in pretty good shape. Now, I think this will help if I actually do a problem here with actual numbers, so we can kind of start to make sense of this a bit more. Okay, so let's try an example. So this example here is this example up here in the notes. We're going to do this problem right over here, but I just want a little bit more space to work with. But know that we're trying to use a 4th degree Maclaurin polynomial to approximate cosine of pi over 4. Now, before I do this problem, I want us to all kind of pretend that we don't know how to find the cosine of pi over 4, right? Because if you are in a calculus course, hopefully by now you do know what the cosine of pi over 4 is, but we're going to just start with a really basic function here so I can easily model for you how to quickly find the Lagrange error bound. And then we're going to use that process for more difficult functions later on down the line. All right, so let's try a problem here. So starting with, so again, let's find the 4th degree. So let's find the 4th degree Maclaurin polynomial of cosine of pi over 4. That's our problem here. So what does this 4th degree Maclaurin polynomial look like? Well, I know that for a 4th degree Maclaurin polynomial period, I have the following. We can just use our elementary series to say this is 1 minus x squared over 2 plus x to the 4th over 4 factorial, or we can just say 24, okay? Now let's evaluate this 4th degree Maclaurin polynomial at pi over 4. So all that means is I'm going to plug in pi over 4 for x. This is over 2 plus x, this is pi over 4 to the 4th power, all of this over 24. And if you have your calculator, pause the video right now and go ahead and calculate this on your own. But you should get approximately 0.707429. So what we're saying here is that this 4th degree Maclaurin polynomial gives us an approximation for what the cosine of pi over 4 actually is, or what we think it is. We're saying it should be approximately this value. Now, the next part is for us to think about how can we find the error of the series. So we're going to say, all right, now let's find the Lagrange error. Okay, so let's find the Lagrange error, and I'm just going to write LE for short. So the Lagrange error bound says that this error is going to be less than or equal to the n plus 1 order derivative, or the next unused term, evaluated at some z times x minus c to the n plus 1 power all over n plus 1 factorial. Okay, now since we're talking about a 4th degree Maclaurin polynomial, that means we are going to be calculating all of this should be equal to 5, right? That doesn't really look very good. All of this should be equal to 5. So we're looking at the 5th order term. Now, let's pause and let's think about this part over here. This is the part that we really want to concern ourselves with. So we want to find the 5th order derivative evaluated at some magical z value. Well, first, let's find the 5th order derivative. We know that f of x is equal to cosine of x. That means f prime of x is equal to negative sine of x. And I'm not going to write out all of them, but if you just go down the ladder, if you will, we see that the 5th order derivative of cosine x is negative sine x. It's sort of cyclical. Not sort of cyclical. It is cyclical. It comes back to negative sine of x. So this f to the n plus 1 order derivative, or the next order derivative, evaluated at some z. Now, let me do this in a separate color because we're kind of pausing to think about this for a second. We're asking ourselves, what is the, instead of n plus 1, what is the maximum value? What is the maximum value that, or the absolute maximum value that negative sine of z could be? What could that be? And remember what we know about z. We're saying that if x is here at 0, since this is a Maclaurin polynomial, our c value here is 0, and our x value here is pi over 4, that's where we're evaluating this function. We're asking ourselves, where is the z value? That's going to produce the largest possible output for negative sine of z. Now, again, this is where we kind of have to pretend like we don't know, because clearly you're looking at this and you're saying, well, I could use pi over 4, but again, if you knew what the sine of pi over 4 was, then you probably know what the cosine of pi over 4 is. And if you know that, then why are we even doing this problem to begin with? So we're not concerned too much with trying to struggle to figure out where that z value is between 0 and x. Instead, just ask yourself, for the sake of this problem, what is the largest possible output for the sine function? The absolute value of negative sine z. What's the largest possible output that we could have? Well, it's 1. We know that the range of sine is 1. So this is the largest possible value that m could be. So now that we know that m is 1, we're going to use that to calculate the rest of our Lagrange error. Now again, could you use pi over 4 here and end up using negative root 2 over 2? You could, and it would not be wrong. In fact, when we're doing Lagrange errors, depending on what you use for your m value, as long as it's reasonable, you're going to get a number of different possibilities. But again, we're concerned with trying to find the worst possible error here to a reasonable extent. So our Lagrange error, and then let me just go ahead and bring this down because we're going to use this. Okay, so our Lagrange error here, we can say the following. It is less than or equal to this fifth order derivative evaluated at z. I don't know what z is, but I know the largest possible value or output of this fifth order derivative is 1. We know that our x value is pi over 4. Our c value where our function is centered is 0, and we're raising this to the 5th power. And this is all over 5 factorial. And if I want to just clean this up a little bit, I can just say pi over 4 to the 5th power all over 5 factorial is going to be approximately equal to 0.00249. Okay, so this Lagrange error, we're saying, all right, my 4th degree Maclaurin polynomial, let me just go back, our 4th degree Maclaurin polynomial, which we said was 0.707429, it's going to be off by the actual value of cosine of pi over 4 by no more. In fact, it's going to be less than this amount. This is the most that we could possibly be off by. Now, let's quickly just check to see how good was our approximation. How good was our approximation? Well, if we actually take the cosine of pi over 4 and we subtract what we found, our, let me write this a little bit better, our m sub 4 of pi over 4, basically our approximation that we got here, this 0.70429, if we actually subtract these, we see that our actual error is way smaller, our quote-unquote actual error, because again, this is obviously an approximation, but we see that our quote-unquote actual error is way smaller than that. So even though our Lagrange error looked really good at the beginning, we're like, hey, we're pretty good to 2/1000ths of a place, our actual error is way smaller than that. But again, that's fine because this is to give us the largest possible error that we could have. So hopefully this gives you a sense of how we're using our next term, similar to the alternating series error, to find the error for a series that may not necessarily be alternating. Okay. Take a moment now and try some of the other problems in the notes and check your solutions in Google Classroom.